Today's episode is called Chaining, Routing, Parallelization, 3 ways to wire atoms together, and the one place you buy reliability. So, your instinct on a hard task is to have one prompt that asks for everything. You have our does the read PDF, extract 14 fields, match the PO, check tolerance, flag duplicates, decide, post or hold, and you do it with one prompt. So 6 jobs, just send that one call. And if you look closely, reading the PDF is actually perception. Extract the 14 fields is also extraction. Sorry, the first one was perception. Match the PO is lookup. Check tolerance is arithmetic. Flag duplicates, post or hold. And if you look at them, these are all different skills. And you just want to launch it with one set of instructions. And you're expecting one output. So there was a research, and this is published, that when state-of-the-art LLMs are tasked with multiple heterogeneous subtasks in a single prompt, their accuracy declines compared to processing each instruction separately. But there is a second problem, quieter than accuracy, and it is the one this episode is really about. One call produces one output if the PO number came out malformed at ask 3. If it came out malformed at ask 3, nothing notices. So ask 4, 5, 6, they are just built on that problem that is already here. And then all of this is screwed because you have the problem that's not fixed early on. So the first fix everyone reaches for is basically to make the model think out loud. This is what we call chain of thought. So you tell it, hey, think out loud, work through it step by step, show me how you would be reasoning, instead of just jumping to an answer. And it writes its reasoning first. So if you look carefully at the step, because this is the part people miss, it's still one call. So you have this one call, and it gives you one answer out. One prompt goes in, one prompt comes out. The reasoning steps are inside that output, and they are basically text. What it buys you is real. So the model conditions each new token on the reasoning it just wrote, and you're giving it, in a way, more context, more possibility to think about its own input. So it stops leaping to conclusions. And multi-step problems generally improve. Like you literally can, there is research. What it does not buy you is any structure. These steps are tokens. They are not really objects. No code can reach into step 2, test whether that PO is well formed, and stop the chain. Basically, your program sees one blob of text. So chain of thought decomposes the reasoning, but it does not decompose the system. You still have one call, one output, nowhere to look, and hold onto one number. On the scan benchmark, chain of thought scores 16.2%. We will come back to it soon, like in the upcoming slides. So here, what you would do is that you would do it for real. So you have separate calls, extract is one request, match the PO is another, third one is decide. And look what appears, our nice gate, something we have spoken about in previous episodes. So you have a gap. That gap that is created in your code is where you'd have ordinary code running. So what goes in it is basically if the PO number does not match the expected pattern, route this invoice to the queue, for example, or anything, any check you would have that is made of deterministic codes. You would have a schema check, a range test, a database lookup, anything to sort of ground your own model, give more context to your model. Not more context, but introduce regulation to your model. And either it passes or not. So one thing I wanted to say, many people would say that you decompose to make each step easier, which is true. But what I would say is that it's actually this decomposition makes you add the gate. So the decomposition is, you need to make the decomposition with the gate in mind, because that's also very important. Don't make the decomposition just with the context in mind. You make the decomposition with what should be my gate. That's the question you need to ask yourself when you're making the decomposition. Actually, I would say even trying to get this gate as being parallel to other use cases where you have code that is, or a similar solution would be interesting, would be nice because you don't need to re-engineer something new. So actually, Anthropic supports the mechanism in their own words. You can add programmatic checks, see gate in the diagram, or any intermediate step to ensure that the process is still on track. They said programmatic, not another call, and the gate can do 4 things: pass, retry the step, hand it to a human, or stop the chain. So from here, for the gate, this is something we talk a lot about in process mining or the previous videos. So this introduces us in another door of when to introduce human in the loop, when not, why would I do that, why not? So this is bigger question that I'm talking about in my other videos. So the pattern formally is prompt chaining. So prompt chaining, which decomposes a task into a sequence of steps where each LLM call processes the output of the previous one. So when to use it? The task that you need to use this for can be easily and cleanly decomposed into fixed subtasks. Fixed means you can write the list of steps down in order before a single invoice arrives. If you cannot write that list in advance, this is a problem. It's the wrong pattern to choose. And actually, episode 6 is for you. And the trade is explicit. You trade off latency for higher accuracy by making each LLM call an easier task. So 2 calls take longer than 1. You are buying accuracy with time, and as we just saw, with somewhere to put the check-in. So, and every call takes more time, but you get also that check-in that we have been, like that gate that we have been talking about. Next, how large that easier task effect actually is. Because the research number is bigger than what people are expecting, actually. So now we introduce a new concept, which is the least to most prompting, which is chaining with a rule about order. So basically, the idea is that you would solve the easiest subproblem first and let each answer feed the next. And it runs in 2 stages, actually. And the 2 stages are the core of this idea. First, stage 1, you do not ask for the answer at all. You ask the model to list all of these. You just tell it, hey, tell me how all of these work. Which fields exist on this invoice? What is the PO number? What does that PO say? Does the total match with intolerance? That list is, in a way, your planning. After that, you solve them in order. What is meant by that? Interpret calls, and each answer is passed forward as input to the next. So here, you solve the first question, and it's actually a difference between chain of thought. So you solve this, and then that would feed this one, and you solve this, and then, and no matter how many problems to solve that you have. When you solve subproblem, the actual answer, so this is the difference between chain of thought. Chain of thought, you're just writing a text, trying to discuss like the whole problem, like the whole bigger problem in that text. From in least to most, you're literally solving each problem separately and waiting for it to fed to the next one. So how much does that matter? On the scan benchmark, all splits with 14 examples, thought scored 16.2% and least to most 99.7%. It was the same model, same problems. The only change is where the decomposition lived. And that's the whole reason why least to most is important to know. So least to most has one general solver walking through subproblems, and you're basically decomposing the problem and prompting, asking a different question at each time, and generally the solver is asking itself, what if each subproblem has its own specialist? So you build a library of prompt modules. So it's like a split module that breaks a document into line items, and a lookup module that fetches the PO record, a compare module that checks totals against tolerance, a dedup module, and a controller that sits on top. So you have all of these modules that you can use for resolving the problem that you have. Why this matters, and this is very important. Each module is independently optimizable. It can be tested, tuned, swapped, or replaced by plain code. So here, this is what is usually used. These are the modules. Of course, change can happen. people could find a new type of module that would be smart to have. Things can happen. So it's a very modular build. And on the other side, there is this paper that said that a module can itself decompose further. So it came from CLR 2023, and it is that the last stop before subtasks, sort of, you can just, for each module, you would have more branches, different possibilities of where that branching would happen. So split, lookup, compare, until you go and find the most undividable subtask, or you would be rather not divided, because then it would be like losing something to your problem. So honest ledger, because chains are not free, and I think if you were concentrating and watching this episode, you would know that this would create problems, like the least to most or whatever pattern you're going to be choosing. The first cost is latency, and it's going to be adding up serially. So let's say you have 6 calls in a row in 6 trips, and each time you're sort of like this needs to wait for this one to finish so that it can hand off the work. And this can only start when this one finished and already delivered its results. So that's the first problem. Second is that every handoff, every step is is a new failure point. Let's say at 95%, every time you're at 5 steps, you're at 77%, then you have 59% reliability, which is not great, 20, yeah. So having chains comes at its own risk. It's nice because it decomposes the problem. And real systems basically land on both sides of that curve. So retries push it up because your correlated failures, and correlated failures push it down. What survives is the direction. So generally, you don't want to have too many nodes in your chain, which is exactly why the discussion that we already had about the gate is very important, because it interrupts the decay, and a chain with no gates in it is just a longer single prompt with more places to go wrong. Now for pattern number 2, and this is what we call routing, which is basically you're just classifying an input and directing it to a specialized follow-up task. So you have a classifier, and it's basically what it tells you. So in, you get the customer message. Out, you get general, refund, technical, for example. And from there, what happens is that you're gonna, depending on that classification, you're gonna take it these different paths. General would be just FAQ prompt plus docs. Refund request, you get policy prompt plus ledger tools, and so on and so forth with technical support. And it's basically, this is from Anthropic, they call this sort of concerns. So why not just prompt all of the 3? And in their own words, without this for one kind of input, it can the performances on other inputs. So think about what happens if you try to serve all 3 from one prompt. Every refund rule you add makes the prompt longer and vaguer for the FAQ case, because you're preserving the context from the previous prompts, So every tech support instruction would get diluted. It would dilute, for example, the refund logic. In a way, routing is like building a team in a tech job. Each one is doing their own job. It's really hard to make everyone do the same job. So the second use of routing is money. And this is something I will make a longer series about, because everyone is making models and everything, but they don't think about the economics of what they're implementing. And that's the best way to go bankrupt. So there is a paper from December 2024, and it says routing easy or common questions to smaller models like Claude 3.5 Haiku, and hard or unusual questions to more capable models like Claude 3.5 Sonnet to optimize cost and speed. It discusses already this routing capability and cost per token. Anthropic has since actually refreshed that line with newer models, names, and the change, so it's always an evolving list. And the goal is to optimize best performance to cost per token. I use the original because cost and speed is what the research actually measures. So it measures well. So Root LLM from Berkeley and LMSys published at ICLR. And they are talking how routing between a cheap model and GPT-4 gave cost reductions of over 85% on empty bench, while still achieving 95% on GPT-4 performance for everything. So look at those bars. You're reducing 85% with just a good routing decision. You keep all of the quality, a seventh of the spend. It's amazing. Now the failure mode, because routing has exactly one and it is structural, it's the good old misroute. So the refund request gets classified as technical support, and even if the technical support does excellent work on the wrong task, but the problem is that nothing errors and nothing retries. The issue here is that basically the classifier is the ceiling of your system, and you do not see the costs. It's maybe bad outcomes, less customer satisfaction. This is not something you would see on billing report. This is more something you would see through empathy and working with your clients. So there's not something I would tell you. There's not a paper or anything like that. It's more like engineering reasoning plus practitioner corroboration. So it's not the theorem on root LLM. Now for pattern 3 is that LLMs can sometimes work simultaneously on a task and have their outputs aggregated programmatically. So sectioning is you take a task and you break it into independent subtasks and then you run them in parallel. Of course, they need to be independent from each other because that's the whole point of this. Otherwise, you would have a chain. So what you do is that you'd have the query, you split this and this, they would run on parallel, and then you'd go from here, here, and you'd have the output of these two would feed into this one, and this one would judge the output. And it's better than having one prompt where you're telling your LLM to decide on its own, and because you're pulling it in different directions. Having the two outputs and having an aggregator gets you better results, of course. And the mechanics here, to budget with. Latency is basically roughly the slowest branch, meaning that work log drops from the sum of the two calls, to the maximum, the one that took more time than the other. That is a win. On the cost side, you are paying basically for more branches you are launching. And the note on a famous number, cut research time up by 90%. So this comes from Anthropic's multi-agent research system. They are saying that you're cutting research time by up to 90% by doing this, which is generally an amazing figure, of course. I wouldn't argue otherwise. So the second variation of our third pattern is voting. And it's the same task that you're prompting multiple times to get diverse outputs. Note that carefully. So not different subtasks, the same question that you ask n times. There is a difference here. So the mechanism is that you send one task, sample several independent reasoning paths, and each path returns its own answer. Here, say for example, would say post, one says hold, then you have a code. So here you're having code. It's not a model that's judging. It just says, okay, you have n diverse reasoning paths. I'm just gonna see which one, like a vote, and here post is basically winning. We're having more post than hold. And this is the trick of the whole thing, is that mostly why voting works, why it gets good results, is that when it's wrong, it needs to be wrong in the same specific way so that it's repeatable. So if it happens one time, it's just a superfluous coincidence. If it happens many times, then it could be problematic. So it is well-measured technique, proven through academia, especially in the ICLR 2023. So we could see it in GSM 8K, got better results, 17.9 points more than against greedy single path decoding. So these are different techniques. And there is a distinction here. Voting here is what we call unweighted majority. We don't have a verifier. Best of n, you have a verifier or a reward model that picks the winner. What I'm meaning by that is that you would have a model that's scoring the candidates and picks a winner. It's not. So this one is just code, is basically whatever gets more grading, and this one you get LLM as a judge. And as usual, the cost is n times tokens, which is not great, but yeah, for critical tasks, it's one more check that you could add. Now, for the references, I'm gonna show you a table, and this table is derived from each pattern's mechanics plus the specific number we just covered. There is no single benchmark, all 3 patterns on the same task. Nobody has run it. It could be a nice paper. Frankly, I'm so busy I can't do that, but yeah, it would be interesting. So we have this table. This is coming from all what we discussed until now. Why the latency, basically what you're winning, what you're losing, the cost, what you buy, what's the positives and the negatives, and the effect on latency. The vocabulary now is coming across vendor, and what's happening is that there is sort of convergence on what each of the vendors should be providing to the programmers. So LangGraph produces all 5 patterns on their, they have it available. Google's ADK ships them as actual classes: sequential agent, parallel agent, loop agent, and calls parallel agent the fan out, calls it to fan out and gather pattern. And OpenAI agents SDK makes the same case for the workflow side. Orchestrating via code makes tasks more deterministic and predictable. You have the sources here on the screen. So you have 3 fences, and none of these are agents. So it's not about agents. Right now we're talking about all of these are workflows. They have predefined code paths. The router is the tempting one. We already have spoken about this, like whether it's the agent or not, but the router, you're making a decision from available branches. So it's not what you'd call max agentic, because the solution space is already defined for you. So I would say check this out, read it, take your time, because this is what you have been talking about. One little thing about voting and how it's different from multi-agent is because, so Must is talking about you have inter-agent failures that are being provoked. What's nice about voting is that it's not agentic, it's not reliant on orchestration, it's basically just voting, So, and those inter-agent misalignments are usually very nasty, and they are really, really bad to prevent in production. So generally, there was this argument from Hong Won Chung. Sorry if I tortured that. And it says, don't teach, incentivize. You add structures suited to your current compute, and it becomes the bottleneck at the next. So today's gates may be tomorrow's scaffolding. The decision rule survives. Where do you place? The question is, where do you place the check? Meaning is that the gates you add now may be later used as context for the building, for the model, as model context for your next iteration on your product. And he's talking here about model architecture, not agent gates. And the harness version of this is the practitioner's community extension. But even granting it granting a harness full decision-making power and, full context, the decision rules would survive even if you give the harness the full control. So the gates that you already have are really important to set in the beginning, maybe even without agents. You should maybe code them by hand, So where do you place the check is basically a question that you should always keep asking, whatever the answer that turn out to be. So always go back to your basics. Always think of it related to the context where you're implementing your agents. And now these are the 3 points that we discussed in this episode. Keep them in your mind. This episode has been longer than the others, so yeah. Please like and subscribe, and follow me on LinkedIn if you like my content, and see you.